read table page 189? What does all the red writing refer to? The Z groups. So some are very straightforward Z groups, some are a lot more complex. They can be very complex. Alright? Now, what are they showing us up here? What are they showing us up here? Or down here. What are they showing us basically? Okay, so this thing here, we can refer to as a dipeptide. We can refer to this as a dipeptide because of what? A di means two, yeah? A dipeptide has got a peptide linkage. Remember the amide linkage? The amide linkage can also be referred to as a peptide linkage, right? It's formed. What sort of a reaction is required to make an amide linkage? A condensation type reaction. So you get the carboxy group of one amino acid reacting with the amino group of the other amino acid. This is in red. This is in red because these come off, don't they? And you've got the link happening between the carbon and the nitrogen. These three atoms coming off form your water. That's one single peptide linkage made. So a dipeptide will have one peptide linkage. A tripeptide would have two. Okay? And so on. A polypeptide would have many peptide linkages. A protein, a polypeptide, if you like, is the stepping stone to having made a protein. I can't remember the top of my head. It's like 1,000 amino acids, I think, will give you a polypeptide. Tens of thousands of amino acids will give you a what? A protein. A protein is basically a large version of a polypeptide. The smallest version of a peptide is a dipeptide. So it goes amino acid, dipeptide, polypeptide, protein. Okay? So that's obviously very important for you to understand what a peptide linkage is. Yeah, on page 195, yeah?
On 192 it says that at least 50 amino acids.
There you go. Now on page 192, a polymer. So halfway down the writing on page 192, can you see where it says a polymer made from amino acids is known as a polypeptide? Okay. And polypeptides built up from more than 50 amino acids are usually called proteins. So there you go, I was exaggerating quite a bit. So up to 50 amino acids is a polypeptide. Any more than 50 amino acids can be referred to as a protein. Alright? So probably the most important thing there is the peptide linkage, or the amide linkage. You must memorise how that is made. Now, the next most important part in this chapter is page 193. Page 193, which is this thing here. This table here is very, very important. Okay? And it's a very nice summary of what we mean by the primary structure, secondary structure, and tertiary structure of a protein. Okay? So, big circle around this table. This must be memorised. Primary structure, well, you can see according to the table, the most important part under primary structure is the opening line, the order of the amino acids. That's it. The primary structure of any protein simply refers to the order of the amino acids. So if a protein is given to you and they're asking you to write down the primary structure, all you need to do is write down the order of the amino acids. That's it. That's all primary structure refers to. The specific order. Now, a lot of this stuff that we're going to be talking about here refers to another biomolecule, being which one? There's one more biomolecule which we haven't looked at, DNA. Primary, secondary and tertiary structure can be used for proteins and is also used for DNA as well. Okay? So, obviously these things here, what are these things here? Each little colour here represents a specific amino acid, yeah? histine, leucine, valine, glucine, whatever, right? So they're all different amino acids. So the order is the primary structure of it. Okay? Now, the primary structure is very important because it determines what the overall, what is going to be of the protein. Yeah, more shape. The shape of the protein. Now, the shape of the protein is very important, isn't it? Because, can you give me an example of a protein? What do we refer to? What's the name of a type of protein that can be used to speed up biological reactions happening within a living thing? Enzymes. Okay? So enzymes are one specific type of protein. There are thousands of different enzymes. But proteins can be enzymes. They can be structural protein. For example, keratin in hair. It's not an enzyme, but it is a protein. It's a structural protein required for structure. Enzymes are proteins which catalyse biological reactions. Now, enzymes are very specific. Okay? There is one enzyme, for example, for the hydrolysis of starch. There's another enzyme for the hydrolysis of whatever reaction. Specific enzymes for photosynthesis, for example. Specific enzymes for respiration. Specific enzymes for DNA replication. Right? Specific enzymes are required for specific reactions. So, can we say all proteins are enzymes? No. But can we say all enzymes are proteins? Yes, we can. Okay? So that's the one. Now, if you change the order here, if you change the primary structure of the protein, well, there's no way that enzyme, for example, will continue to speed up the reaction that it used to speed up. Okay? Very dependent on the primary structure. Now, secondary structure is the next thing. The most important part in there is the opening sentence again. Parts of the chain can attract each other, creating particular three-dimensional shapes. Now you can see here, there is, okay, here's the primary structure, and now here we see some coiling happening within the primary structure. What's the coiling due to? Okay, these broken lines are definitely hydrogen bonds. So the secondary structure of a protein is determined by the hydrogen bonds that occur between the carbonyl part of the carboxy group, which is left over. Remember with the carboxy group, the OH came off? What's left over? The C double bond O. You remember on the NH2 group, the H came off? What's left? The NH. So you will get hydrogen bonding happening between the oxygen and of the carboxy group and the hydrogen of what's left of the amino group. You'll get hydrogen bonds happening there. Now, depending on the number of hydrogen bonds you get, that'll determine how tightly coiled or how loosely coiled it is, yeah? So that contributes. So that contributes to the overall shape. This contributes to the overall shape of it. There are three things that contribute to the overall shape of the protein. Shape is the key. Order, hydrogen bonds between the O and the H of the functional groups. Very important, okay? And this is keratin, for example, in hair and wool. Give these. So basically, with curly hair, for example, keratin is the major component of hair. With the curlier hair is, the more hydrogen bonds you have. And this is why when you have if you haven't had a shower for a couple of days, your hair tends to get messy and all over the place because you're getting more hydrogen bonds forming within the keratin. You have a hot, warm shower, some of these hydrogen bonds are broken. What happens to the keratin? Is it as tightly coiled, or does it loosen up a bit? It loosens up a bit, and that's why it's more manageable to brush your hair. Yeah? So that's an example of, a real life example of what these hydrogen bonds can do. Okay? But if you're born naturally with curly hair, you've got a larger amount of hydrogen bonds within each sequence of amino acids than someone who has got straight hair. Okay? Okay. So that's the secondary structure. Now, the tertiary structure here. Tertiary structure. The tertiary structure, what's that due to? Opening sentence. Z groups. We haven't mentioned anything about the Z groups here. We haven't mentioned anything about the Z groups here. The tertiary structure is due to the types of Z groups present. Now, because every protein is going to have a different primary structure, yeah, you're going to have different Z groups there. Therefore, the interactions that happen between the Z groups will also be different. So the opening sentence, under tertiary structure, the Z groups in the amino acid of a protein molecule influence the overall three-dimensional shape of the molecule. So this influences how tightly coiled the coil will become. The overall three-dimensional shape, as you see here, yeah, is determined by the interactions between the Z groups of the different amino acids present. Okay? So if you get a Z group up here, in an amino acid here, or if you get the Z group here of this amino acid interacting with the Z group of this amino acid here, obviously it's not going to be straight, is it? It's going to bend over. So it's those interactions that determine the overall three-dimensional shape of the protein. Okay? So under tertiary structure, you've got 3 dot points. Okay, you've got the first dot point, you can get, it says, hydrogen bonds between polar Z groups such as those containing OH and NH. Do you understand that? So if you've got a Z group here with involving atoms of oxygen, hydrogen or nitrogen, and another Z group here with similar sort of atoms, you can get a hydrogen bond happening, yeah? Between the Z group from here and the Z group from here. So hydrogen bonds is one type of interaction you can get between Z groups of the protein. You can also get, second dot point, very important, ionic interactions between a Z group that contains NH3 plus and another one that contains COO negative. When does that happen? You remember what we said about amino acids under acidic conditions and under alkaline conditions? Remember that? Zwitterions, yeah? Okay. If you've got a carboxy group in a Z group, if you've got the COOH carboxy group within the Z group, all right? Under alkaline conditions, that COOH is going to become what? Under alkaline conditions. Alkaline means there's not many H pluses around, yeah? So they're going to give H pluses. So the COOH becomes COO negative. Okay? If you've got an NH3 plus happening in another Z group of the same protein, you can get an ionic interaction, positive and negative. So if you look at the table, for example, in 1.9, can you find any Z groups where that would occur? Look at the table on page 189. Can you see where any ionic interactions could occur?
Glutamic acid.
Which one?
Glutamic acid.
Glutamic acid, if you have, yep, has got, see how that's got the carboxy functional group there? Yeah? So if that all of a sudden becomes COO negative, it could form an ionic interaction with with glutamine, which has got the NH2 group, which could become NH3 positive. Yeah? Because if our example was alkaline conditions. If it's alkaline, not many H pluses, but so the COOH becomes COO negative. Well, the NH doesn't explain why the NH2 becomes NH3 positive, but that can happen, all right? You can have Z groups with NH3 plus, other Z groups with COO negative, you get an ionic interaction. That's all you need to know about that. And Then the third dot point. So we've so far got hydrogen bonds that can happen between Z groups. We've got ionic interactions that can happen between Z groups. What's the third one that can happen? You can get covalent bonds happening between Z groups. And the example that they refer to here is what we call a disulfide link. A disulfide link. So you need 2 amino acids which have got sulfur atoms in them. Can you see any there in the table? Cysteine. Cysteine has got HS. If it loses the H, if it acts as an acid and loses the H, it's big, yeah. And methionine has got sulfur atom there. So you can get covalent bonds happening between 2 sulfur atoms, for example. Sulfur is a non-metal. Yeah? So if you've got two non-metals together, the only bond that can form there is a covalent bond. So you get what these things, a disulfide link happening. And they can also be referred to as disulfide bridges. Yes?
How would methionine or whatever it is form a sulfide link? Because it's got the sulfur, but most of it...
Yeah, no, that one wouldn't. That one wouldn't. No, that one wouldn't.
Okay.
But cysteine definitely, because it's at the end of the chain.
Yeah.
Any others there? There might be some other ones at the end of the chain. No? Okay, so you'd need two cysteine amino acids. And we're talking some enzymes, proteins got thousands of amino acids. All right? 50 amino acids is a very small protein. Most proteins are thousands of amino acids. So chance of having heaps of cysteine amino acids in there is very high. So the opportunity for disulfide links is very high as well. So that's the third type of linkage you can have between different Z groups. And then there's the fourth one, which is present in everything basically, being what? Dispersion forces. So if you've got non-polar Z groups, okay? So with the polar Z groups you get the hydrogen bonds, with the non-polar Z groups you get the disulfide links. Okay, valine and phenylalanine. If we look up valine, see valine? See the Z group of valine? Can you tell me why that's regarded as a non-polar Z group? Can you tell me why valine is a non-polar Z group? Just focus on the red part.
This is a hydrocarbon.
Yeah. And it's also symmetrical, yeah? And what about phenylalanine? Straight out hydrocarbon, yeah? Straight out hydrocarbon. Okay? They're non-polar. So you can get dispersion forces happening. Can you understand how these 4 different types of interactions between Z groups can also contribute to the overall shape of the protein? Yeah? So that's your primary, secondary, tertiary structure of proteins. Very important. Okay? So that page there is ultra, ultra important. Page 194 now. So page 194 is the enzyme, a little bit on enzymes. Okay, so in my book, what have I highlighted as the most important? On page 194, basically the opening paragraph, see where it says the biological catalysts that accelerate the rates of chemical reaction in living things are a type of protein called enzymes. So highlight that. Very important. Middle of the first paragraph. Okay, so are all enzymes catalysts?
Yeah.
Yes, because they speed up the rate of any reaction, of a biological reaction. Are all catalysts enzymes? No. In industrial chemistry, the catalysts are never enzymes because biological reactions happen at body temperature, yeah? Okay? 30, 40 degrees Celsius, max, maybe, right? That's the temperature that enzymes need to operate at. Okay? Industrial reactions, which is what we're going to move on to later, very shortly, happen at temperatures of 200, 300, 400 degrees Celsius. You put an enzyme in that situation, what's going to happen to it? Denature. Okay? So, all enzymes are catalysts, but not all catalysts are enzymes. Okay? All right. The next thing I've highlighted on page 194 is the first dot point compared to inorganic. So these are the organic catalysts. Enzymes are the organic catalysts. And now it says a comparison, but it's basically what we just said. Compared to inorganic catalysts, first dot point, enzymes produce much faster reaction rates. That's interesting. Okay? An enzyme, which is a biological catalyst, increases the rate of a reaction so much more than what an inorganic catalyst does. Why? Because our body needs instant energy for everything, yeah? The biological reactions have to happen quickly within a living organism. Okay? We can wait a couple of days in industrial chemistry to produce a particular product. Not an issue. Okay? This is why enzymes are so much more efficient than inorganic catalysts. Okay? And it gives you an explanation there. That's very important. Second dot point, enzymes operate under much milder conditions. We already mentioned that. You put an enzyme in 400 degrees Celsius, it's finished. Third dot point, much more sensitive. Enzymes are much more sensitive. Sensitive, what does it mean by sensitive? The catalytic activity of many is destroyed when they are heated. Okay, we already mentioned that. The enzyme. I thought the next one is what I was thinking of. Okay, so they're more sensitive. Yeah, we know that. Fourth dot point, at the top of the next page. Enzymes are very selective. This is a very important one. That's what I was trying to say at the beginning, yeah? What do we mean by being selective? For one specific type of reaction. Okay? The enzyme which is responsible for the breakdown of starch will be completely different, or will not be able to speed up the breakdown of cellulose, for example. Okay? Or the enzyme responsible for, the breakdown of fat, hydrolysis of fat, will be not capable of hydrolysis of starch. Very, very selective. In industry, however, an inorganic catalyst can be used to speed up the rate of a number of different reactions. They're not as selective. Okay, that's one major difference. Yeah, coming up.
That's cool.
Coming up. First of all. Okay. So we right with that? Organic catalysts, very selective. Inorganic catalysts, a lot less selective. Okay. Now, why? Why are biological or organic catalysts, enzymes, why are enzymes so selective? Yeah.
Because they have to be, otherwise they might end up killing.
They have to what?
They have to be selective because they can't destroy the wrong things.
Yeah.
Break apart.
But how is it that they're so selective?
Because they have to do it so fast.
Shape of the active site.
Shape. Look at there's a picture there. Yeah? Page 195. Okay? See the enzyme? There's a nice simple picture there. Enzyme in orange or whatever. In step A. And then and the green thing is the substrate. What does the word substrate mean? It's the molecule that the enzyme attaches to. Okay? For an enzyme to speed up the rate of any reaction, it must attach to the original molecule. Okay? For it to attach to the original molecule, it must have a specific what? Shape. Does any key open any door? Well, master keys don't exist in living organisms. Okay, so maybe if you ignore master keys,
inorganic catalyst.
a master key can be can be imagined as being an inorganic catalyst. But normally, a key is designed to open one specific door. It's what we call the lock and key method. All right? It's actually used. That terminology is used to define the operation of enzymes. So, enzymes have a lock and key mechanism. The shape of the enzyme's active site, okay, the part of the enzyme which attaches to the molecule that it works on is referred to as what?
Wait, what was the question, sorry?
Yeah. The part of the enzyme which attaches to the actual molecule that it works on is called what?
Active site.
The active site. Every enzyme has got a different shape active site. Okay? A different type of active site. Okay? This is why enzymes are so specific and so selective. Alright? So, in that picture it shows you you've got the enzyme attaching to the molecule that it's going to work on. Once it attaches, how does it attach? What's the diagram showing you? What's the diagram showing you?
The bond.
Hey? Yeah, bonds. Yeah. Here's the enzyme with its specific active site, which fits nicely with this substrate, the molecule that it's working on. But to remain attached to it, it must form bonds with the substrate. Those bonds can be different types of bonds, which you need to be very aware of. Okay? It's not uncommon to get an exam question where you are asked to specify the bonds that will form with a particular enzyme and its substrate. They can be hydrogen bonds, they can be ionic bonds, they can be covalent bonds. Okay? You must be able to pick them. So this is very important, which you'll see later. You'll see an example of it. So you must be able to... Okay. So basically, the enzyme will attach to the substrate with its bonds. It will perform whatever it performs. Notice now the substrate has broken up. So this is sort of like for digestion, maybe. Digestion of whatever. Hydrolysis of whatever. The breakdown of something. Okay? It's attached to the substrate. It's shaken it up. This part of the substrate breaks off. It's done its job. These bonds break away now. The original substrate has been broken up into two pieces. Without the enzyme, this could take 100 years to occur. Literally. With the enzyme, it happens in a couple of hours. Okay? This sort of a process is needed for any digestion of any food that we eat, for example. Digestion of proteins, digestion of carbohydrates, digestion of fats. It all involves the breakdown of the substrate into smaller fragments. It can happen without the enzyme, but it'll take hundreds of years to occur. With the enzyme, number of hours, even minutes. Okay? So, this explains why enzymes are so selective. Now, if you have another enzyme with a different active site, if it's got a different active site, it's going to have different atoms around here, isn't it? Because remember, this is the three-dimensional structure of the enzyme, yeah? Different amino acids will give you a different active site. If the active site is different, the atoms at this point, and this point will be different as well. Therefore, the interactions will not occur, will they? Because they're going to be different atoms. So do you understand why enzymes are very selective? Very important. Okay, so now, on that same page, okay, they give you an example. This thing here. Here we go. That was a simplistic, very simplistic version. Here is a more specific version. So figure 12.33 shows the interactions at the active site of the enzyme called ACE, responsible for catalysing a biochemical reaction in which a dipeptide consisting of leucine and histidine is chopped off the end of a short polypeptide chain. Does that make sense? So this procedure that they're trying to show you here is an enzyme breaking off a dipeptide from a polypeptide. So breaking 2 amino acids off from a polypeptide. What's this purple region? The active site of the enzyme. Yeah? The active site now. They're showing that with this active site, there is an NH3 group coming off one of the amino acids here. Okay? There's an NH, there's an O negative coming off one of the amino acids down here, and there's a zinc. If you look up the table, you'll find amino acids with zinc ions, with a zinc atom. There's another amino acid here with a zinc ion coming off an amino acid down here. Okay? So, what sort of linkages can you see here happening between the substrate, this is the substrate in black, and the active site? What's this linkage here called? What sort of a bond is happening here? Which one of those? It's an ionic bond, isn't it? Definitely. You've got an ionic bond happening here. What sort of a bond do we have happening here? Hydrogen bond happening here. What sort of a bond do we have happening here? An ionic bond happening there. Okay? Are there any others? No. So, by these 3 bonds happening, okay, this part of the polypeptide, which continues over here, okay, the polypeptide's over here, this part here is chopped off there, that comes off. Okay? There's how your active site is so important. So in that example, you know, they could give you a question where they show you something like this and you have to find and name the interactions that are happening between the active site and the substrate. Gage.
How would it get rid of them and just form the bonds?
It's due to motion. Yeah, motion. Molecules are constantly in motion. The motion, there's a stronger interaction here, this thing here, this red bond here, and the movement just shakes it off, basically. All right?
Once it breaks apart, how does the bit inside the active site then come out of the...
How does it... Well, I don't know. It comes off. They're not going to ask you that. They're not going to ask you that. It comes off. And then goes and forms something new with something else. Okay? Okay. So there's that. Now, over the page 196, you need to know a little bit about denaturation, which we've already spoken about. But basically, Figure 12.35 is a good way of explaining the graph there. If you look at the graph, figure 12, this graph here, we have effective temperature on enzyme activity. Okay? So here's the rate of any particular biochemical reaction happening within a living thing, which an enzyme is responsible for catalysing. At a temperature of, say, what would this correspond to, say, 10 degrees, the rate is pretty low. At 20 degrees, it picks up a bit. Yeah? At 40 degrees, it's close to its peak. And then all of a sudden, so why does it increase from between here and here? Why does it increase?
Because it's working
Like,
at a better temperature.
yeah, and so what if it's better temperature? Yeah, I know what you're saying. Closer to the temperature of a living thing, and so what?
Higher temperature means more energy and more motion.
More kinetic energy. You increase the temperature, remember the speed of particles, yeah? Increase the temperature, what happens? All particles are moving at all times, yeah? Increase the temperature, increase the movement, yeah? The amount of movement increases, so the amount of shaking gauge that we were talking about before increases. So the breaking off of that little bit will increase. So more motion, more collisions, more reaction. So shouldn't it just keep going? when we get past 40? Normally it would, but not with an enzyme. Not with an enzyme because the hydrogen bonds, yeah, the ionic interactions, the dispersion forces, maybe not so much the covalent bonds, but all those other ones, the ionic, the hydrogen bonds, the dispersion forces that we were speaking about before with the primary, secondary, tertiary structure of proteins, they're all gone after 40 degrees. Or, yeah, they're all gone. So once they go, here's our original protein, look up here. There's our original enzyme. That shape there is needed to catalyse a specific reaction. You go past 40, 50 degrees Celsius, that's what's happened. Can you see what's happened? Yeah? The primary, is the primary structure still there?
Yes.
Yes. The order of the amino acids is still there. Is the secondary structure still there? Not really.
Sort of.
Sort of, maybe. Is the tertiary structure there? These things here are broken. All those things are broken, so you've got that. Now the temperature drops back down to normal. Back down to biological temperature, 40 degrees, 35 degrees. We get coagulation happening. So denaturation means the overall tertiary structure, the overall structure of the protein is stuffed. Denaturation. Okay? Coagulation means what? These bonds, some of these bonds are starting to what? Reform. But have they reformed at exactly the same positions? No. You get the bonds reforming, but not at exactly the same position. So, what's the net effect? Is the shape of this coagulated protein the same as this? No. So, will this one here have the same active site as this one here? No. Is it useful anymore? No. Useless. Different active site? Useless. Okay? So that's what we mean by denaturation of enzymes.
There's more than one in there.
Well, it's just diagram. Yeah, more than one, yeah. But, you know, but they're just trying to prove to you. It's just like the egg white. That's a perfect example of proteins denaturing. You've got the egg white in an uncooked egg. Liquidy, blah, 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 slimy. You cook it, you're raising the temperature way past 40 degrees. When it cools down, it doesn't go back into that slimy, liquidy, whitish substance. It becomes the white part of the egg that you've cooked, yeah? Looks completely different, feels completely different. It's because it's now a coagulated protein. Okay, same thing. Okay. On page 196, again, if you look at the second last paragraph, enzyme activity is dependent on temperature. We understand why, yeah? As temperature increases, the rate of the reaction catalyzed, the enzyme increases. Yeah, we've already discussed that, yeah? Last paragraph on page 196. Enzymes operate effectively within a small pH range. Not all enzymes have the same optimum pH. Pepsin, for example, an enzyme that breaks down protein in the stomach, is most efficient at a pH of 1 to 5. 1 to 5, is it? 1.5. The optimum pH of salivary amylase, an enzyme that catalyses the hydrolysis of starch in the mouth. Lipase, which breaks down, so is at 7.4. Lipase, efficient at 8 to 9. What's that telling us? They have different pH requirements. Why? Because if you have low, you've got to remember this, guys. If you've got very low pHs, you've got lots of H plus ions. Yeah? If you've got lots of H plus ions, the NH2 groups become NH3 plus. Yeah? And if you've got all your NH2s becoming NH3 pluses, you're going to get ionic interactions happening where they're not meant to be happening. Huh? Active site is stuffed. If your pH is too high, what does that mean? Do you have heaps of H pluses or very few? Very few. If you have very few H pluses, something's got to give. What's going to give? You've got to remember this. This is the Zwitterine phenomenon. Yeah? If you've got heaps of H pluses, the NH2s will take them on, become NH3 plus. If there's hardly no H pluses, can the NH2s take them on? No. So what's going to happen? The other one is going to give. What's the other one that I'm talking about? What are the two functional groups involved in amino acids? NH2 and carboxy. So if one does something, the other one does nothing. You understand? So if there's too many H pluses, NH2, all its Christmases have come at once. If there's not enough H pluses, someone's got to give some of those H pluses away. Who can give them? Yeah. NH2 never gives. NH2 is a receiver. COOH is a giver. Okay? Of H pluses. You've got to remember that. So if the pH is too high, that means we've got alkaline conditions, yeah? Do we have lots of H pluses or very few? Very few. The more H pluses you have, the more acidic something is. If your pH is too high, okay, you can't have a lot, there's not a lot of H pluses there. Because it's alkaline. So if there's not a lot of H pluses there, the COOHs will make up for it by giving some away. They become COO negatives. So once again, you're getting ions made, aren't you? COOH is converting into COO negative. That's an ion. Again, ionic interactions where you don't want them. Active site stuff. Yeah? So that's why pH is so important in the operation of an enzyme as well. They give you a quick diagram of a graph of that on page 197. The graph on page 197 shows you, three different enzymes. Yeah, this is the one that happens where? This is the one that happens where? Pepsin, where do you want to say it's at? In the stomach. Pepsin is in the stomach. Yeah? So, in the stomach we know it's very acidic. That's why pepsin works best at 2, pH of 2. Increase it, stuff. Active site is gone. Okay? The amylase is present in the what? Mouth. That's why it works best at about 7. The lipase is lower down in the digestive tract, small intestine, etc. Okay? That's why its peak is there. So 3 different enzymes, 3 different conditions for pH. The temperature, however, would be pretty much the same needed for each, because they're happening in a living organism. Okay? And now, page 197, proteins as markers for disease. That's for your own reading. You need to go through that and understand what's going on there. Have I given you the chapter 12 questions? No, I haven't. How many of them have I given you? None? Okay, write them down. Chapter 12, write them down. So for chapter 12, guys, you need to be able to do 1, 2 and 3. 1, 2 and 3. I'm getting worried, I can't find 4, 5 and 6. What 1, 2? Oh no, that's it. No, I don't want to do 4. So 1, 2 and 3. 7 and 8. So after 7 and 8 you will do, after 7 and 8 you do 13, 14, 16, 18. So 13, 14, 16, 18. Then after 18 you do 20, 21, Then after 21 you do 27, 28, 33 and 42. Right, that's it for that. Now, next lesson we will finish DNA off. And that's it for Unit 3. We'll be up to Unit 4. Chapter 14, we've already done that together, haven't we? Now we get stuck into chapter 15, which is industrial chemistry. Okay. Happy with that, Glenn? Yeah?
You just need something to do with
Why did I make
the
This
is a bit I was looking at YouTube.
It's a bitch.
I'm a big fan of that. No one wants to answer questions. They're selfish.
Oh, I know you, so I respect it.
It's not as wet, I guess. Damn, I don't want to answer. Oh, that's hard.
Don't answer questions.
What?
We don't want to answer questions.
Oh, but you could.
Probably gonna guess.
Probably. How come you like to watch?
Four times.
Why I hate it.
He just does things to smack that guy.
Tell me a story that's not that bad.
Have you met his dog?
No, I'll take a couple of minutes.
He's real nice and
I got it on a box.
That was a bitch.
Oh, I just picked it up
Yes,
for
but
a
not
bit.
nice
Did
dog.
something more interesting.
Also,
it's
not
safe
nice
for
and
you.
nice. Another game, I don't care.
The dogs play pretty well.
Okay.
Doesn't matter, I'm still 1-1. 1 point for a
Yeah,
dog.
they score points. And all the stats are opposite.
Yeah, I'll find the first
Yeah, take a full. Oh, I know. You get the card. Ben, you just make you start meeting the initial dog.
you know.
Because I know what the first one is. Alec and I made a recipe.
What do you mean?